In this video, we're going to give an example of a procedure for which we can control the family-wide error rate. So the first thing I want to remind you is that if we define a procedure, a simple procedure such as reject all the hypotheses with a p-value less than 0.01, then if we assume that all the tests are independent, we can show that the probability of making at least one mistake when we run, for example, 1,000 tests. You follow these equations and you see that the probability of making at least one mistake is almost 1, practically 1, even when all the hypotheses are null. This is not useful. You're almost always going to make a mistake, and you're trying to control that. You want to make that probability small. So another approach we can apply is called the Bonferroni correction. It's quite popular. It's widely used. So I'm going to explain briefly what the Bonferroni correction is. So what we're going to do now is we're going to define a more general procedure. We're going to reject all the hypotheses with a p-value that is less than k. So we already showed that when we make k equal to 0.01, and we're running 1,000 tests, then even when the null is true for all the tests that we are running, then the family-wide error rate is almost 1. That's not very useful. So what we're going to try to do again is try to come up with a procedure for which the probability of v being greater or equal to 1, the probability of making at least one mistake, when all the tests are null, is smaller than, for example, 0.05 alpha. We're going to try to make it small usually. So here's the general idea. Before we get to Bonferroni, I'll explain Zidak's procedure, which is similar. And basically, you can follow these equations. It's not that complicated. This is based on the derivations that we made in an earlier slide. And we can figure out what k needs to be so that our alpha, so that we know that the probability of making at least one mistake under the case where all the nulls are true is 0.05. And in this particular case where we have 1,000 tests, this number, this k, is 0.00005. So that would be our procedure. Every time our p-value is smaller than that very small number, we call it significant. If we do that, if we define a procedure that way, then assuming that all tests are independent, we are controlling the family-wide error rate at 0.05. But this assumes independence. I said that earlier. I said if the tests are independent. And that is not always the case. In biology, many times this assumption doesn't hold. For example, if you're testing many genes and we know that genes work together, they're not going to be independent. So this assumption is no longer valid. Bonferroni gives us a way to control the error rate without having to assume that all the tests are independent. Here are the derivations for the Bonferroni procedure. And basically what we show is that if we define our cutoff as alpha divided by m, remember m is the total number of tests, then we control the family-wide error rate at a level of alpha. So this is the Bonferroni correction, and again, these are the equations that show us that in fact we are controlling the family-wide error rate even when the tests are not independent.